Let's do a quick recap of some of the things that we discussed in this chapter. Amines are derivatives of ammonia. The basicity of arylamines is lower than that of alkylamines. The nitrogen lone pair electrons in arylamines is delocalized by interaction with the aromatic pi system, and therefore aromatic or arylamines are less basic than alkylamines. Compounds that contain one or more nitrogens that are shared in a ring are referred to as heterocyclic amines. Alkylamines are prepared by SN2 reactions of ammonia or an amine with an alkyl halide, or by the Gabriel-amine synthesis. In reductive amination, a ketone or an aldehyde is treated with an amine in the presence of a reducing agent such as sodium borohydride. Amines can be synthesized through the Hofmann and Curtius rearrangements of a carboxylic acid derivative. In the Hofmann elimination, typically amines will undergo an E2 reaction, giving you the less substituted alkene or the Hofmann product. And the Sandmeyer reaction is a reaction that allows us to convert arylamines into several different substituted aromatic compounds by the attack of a nucleophile with a diazonium salt intermediate. Let's go over a few examples of the reactions we covered in this chapter to review these reactions. We'll start off with a reaction involving a nitrile and reacting it with lithium aluminum hydride. In the second reaction, an aldehyde is also reacted with lithium aluminum hydride. In the third reaction, we're going to reduce a nitro group in this substituted aromatic compound with hydrogen gas, palladium on carbon, or tin chloride and an acid. In the fourth reaction, an alkyl azide will react with lithium aluminum hydride. In the last reaction on this slide, we're going to take a ketone, add a primary amine, and sodium cyanoborohydride at a pH of 3 to 4. In the first reaction on this slide, we're taking a nitrile and we add in lithium aluminum hydride, which of course is a hydride reagent that will attack the carbon of the nitrile. It will occur twice, and then the two negative charges on the nitrogen will react with the protons on this acid to overall convert the nitrile into a primary amine. The combination of a hydride and an acid essentially is equivalent to adding H2 gas in a hydrogenation reaction. In the next reaction, we're going to take an amide, and unlike most acid derivatives which react with lithium aluminum hydride, instead of getting a primary alcohol, with amides, we generally get an amine. The reason is the carbonyl is a better leaving group than the nitrogen. So after the addition of one equivalent of the hydride to this carbonyl, the OH that results will be eliminated by the lone pair on this nitrogen, and the imine intermediate will be eventually reduced into this amine. The first two reactions were reactions that we previously discussed in other chapters. We also discussed the reduction of a nitro group into amine. That can be done under hydrogenation or metal reduction. Anytime we add a metal in an acid, it's again equivalent to adding H2 gas. And that will be another method to reduce a functional group such as a nitro group. Azides can be reduced with lithium aluminum hydride and acid. into a primary amine plus N2 gas. The last reaction here is an example of a reductive amination where we take a ketone or an aldehyde. In this case, it's going to be a ketone. We're going to add an amine. We're going to be using a primary amine in this example. That primary amine will add to the carbonyl carbon, initially form an imine intermediate, which would then be reduced by the hydride reagent into an amine. In this reaction, we're going to take an amide. We're going to add Br2. We're going to add Br2 and base. In the next reaction, we're going to use a different acid derivative, which is an azo-acide. We're going to heat it and then add water. Next, we're going to add base to the phthalimide, followed by an alkyl halide, a primary alkyl halide, and then finally hydrolysis conditions, which is base and water. In the next reaction, we're going to add an excess of methyl iodide, followed by silver oxide, water, and heat. And then lastly, we're going to add nitrous acid, sulfuric acid, followed by copper chloride. The first reaction on this slide is an example of the Hofmann rearrangement, which starts off with an amide. We're going to add Br2 to activate the 1,2 alkyl shift, which will eventually lead to the elimination of the carbonyl and combination of this alkyl group on the left of the carbonyl with the nitrogen and the methyl group attached to it. So as a result, we get an amine plus carbon dioxide as a byproduct. The next reaction is a Curtius rearrangement, which involves an azo-azide, which when we heat will be rearranged into an isocyanate. Water will react with it to form a carbamic acid, and eventually it will decompose to form an amine plus CO2, which is not shown here. Notice in this reaction, similar to the Hofmann rearrangement, the carbonyl will be eliminated as CO2, and the alkyl group on the left of this carbonyl would join with the first nitrogen of the azide to form this amine. We're going to lose the second and third nitrogen from the azide as a nitrogen gas molecule. In the next example, we're doing a garyl-amine synthesis where base removes this hydrogen. That will make the nitrogen more nucleophilic. It will attack the carbon with the leaving group. We'll add a propyl group to this nitrogen. And then base and water will lead to hydrolysis of both of these amides, releasing the internal nitrogen plus the propyl group that was attached to it. And then we'll also have the rest of the molecule be eliminated as a dicarboxylic acid. So this carbonyl and this carbonyl will become carboxylic acids. The next reaction is an example of the Hofmann elimination where excess methyl iodide will alkylate the nitrogen to the maximum extent. In this case, we're going to add 2 more methyl groups. Then silver oxide and water will produce hydroxide ion, which will lead to an elimination reaction. The base will remove the least hindered hydrogen on the carbon that is adjacent to the carbon containing the nitrogen. There are 2 possibilities. We can remove this hydrogen on this side or the first one that I drew up here. This is less hindered, so we're going to remove that one. That's typical of the Hofmann elimination. And we're going to get the anti-Sysef or the Hofmann alkene. Last reaction is an example of the Sand-Meyer reaction where nitrous acid and sulfuric acid will turn the amino group into a diazonium salt, which is a great leaving group, and then that will react with copper chloride in a radical mechanism to add a chlorine. On this slide, there are 3 different examples of the St-Meyer reaction. They all start with an aniline, and we're going to add nitrous acid and sulfuric acid. In the first reaction, the diisonium salt will react with copper cyanide. In the second reaction, it will react with hypophosphorus acid. And in the third reaction, the diisonium salt will react either with acid and heat or a copper catalyzed reaction with copper nitrate and cuprous oxide plus water. In the first reaction, the diisonium salt that is formed as the key intermediate in the St-Meyer reaction will react with copper cyanide. That will replace the diisonium salt with a cyanyl group. Hypophosphorus acid will reduce the diisonium salt and put a hydrogen in its place. So this is a good way to remove an amino group. And in the last reaction, we're going to use either acid and heat or a copper catalyzed reaction with water to convert the diisonium salt into hydroxyl group. In this synthesis problem, we're going to convert nitrobenzene into a meta-substituted dihalide benzene compound shown here. In this synthesis problem, we need to convert nitrobenzene into a meta-substituted dihalide benzene compound. This presents a challenge, at least initially, based on the reactions we previously learned. Because normally the halogens are ortho-para-directing, so it would be very difficult to use bromine, for example, to add a meta chlorine. However, based on the St-Meyer reaction we learned in this chapter, we can use an amino group to essentially add other substituents, and the precursor to the amino group, which is the nitro group, as we know, is a meta director. So using that information, we can put the synthesis together. The nitro group we can use to direct the chlorine to the meta position through a chlorination reaction, which we previously learned. So adding Cl2 and iron trichloride will lead to adding this chlorine at the meta position compared to the nitro group. Reducing the nitro group now into an aniline by either hydrogen and palladium or a metal and an acid reduction, we can now get this amino group, which is the precursor to the St-Meyer reaction. This is one of the reasons why the St-Meyer reaction is so versatile. We can convert this amino group into a bromide by adding nitrous acid and sulfuric acid followed by copper bromide. Note that we could change the order of some of these steps. For example, we could add a bromine here through Br2 and iron tribromide. And then when we get to this step, if we add copper chloride, we could add the chlorine and get the same product.